Welcome all. We will move on to the next session, Advanced Electrical Safety Systems and Automation in Industries. Welcome, ma'am, for the next session.
Thank you. Shall I share my screen?
Sure, ma'am. Sure.
Is it visible?
Yes, ma'am.
Okay. Okay, we'll pass on to the second session, that is the Advanced Electrical Safety Systems and Automation in Industries. So, going into the introduction, we know that industry landscape is evolving with the high voltage and high fault current, and increasingly complex systems. Traditionally, the safety methods are traditional safety methods are no longer sufficient for the complex systems which are present now. This presentation will explore how advanced electrical safety systems and automations are crucial for protecting people and their assets. So before going into the advanced technologies, we'll deal with the past and the present trends. So safety measures are the actions, procedures, or guidelines implemented by organization to protect employees, customers, and the general public from harm or injury. It is designed to reduce the risk of accidents, health issues, and environmental hazards within the workplace or while ensuring compliances with safety regulations. The evolvement, the safety practices evolve from the far past, and we are going into the future direction. So we'll focus first of all on the past. The past focus on traditional industrial safety was the primary focus concern was regarding the shock prevention, the circuit protection, the PPE, lockout, and tagout. And the nature of safety measures was mostly reactive one, focused on workers. And the limitations, the measures taken previously in the past will not be addressing complex large-scale systems and the hazards which are invisible, like the arc flash or automation failures, etc. Now, what is the current trend? The present needs, we know that our power system is very complex in nature. We have multiple sources in our grid, maybe the utility, the solar, diesel generators, the UPS, batteries, due to the injection of so many renewable sources. We have multi-source power grid. And the main challenge in the power grid is the synchronization, the load sharing, and fault detection. When we look into the grid, the hazards that may occur are the backfeeding risk, the arc flash, and misoperation due to poor coordination between the sources. For coordinating the sources, we need advanced protective schemes like SCADA integration and real-time monitoring. So for large-scale systems, SCADA the distributed control system, the IoT-enabled devices, all these things have to be implemented. And when we implement such, when we incorporate such automation, there are hazards like malfunctioning of the programs, and operator will be over relied on these particular programs. So such hazards can also occur in the system. Now, what are the emerging hazards? We know that high energy equipments are there in the current system, and we require high voltage switchgears and arc furnaces for them. So we have to integrate, we are having automation in the system, so we have to integrate cyber securities and the other safety precautions. The risk in any electrical network is the arc blast, arc flash, fire, and explosion. So when there are so many automation programs, there are risk of cyber attacks. So cyber physical threats are growing. Hackers are targeting industrial control system for industrial control system. The best example to explain the cyber attacks is the incident or accident Stuxnet, which occurred in 2010. I'll be explaining Stuxnet in the later slides. The future direction. We know wherever we look into, the AI is going at a boom. So we'll be utilizing AI for the safety systems also. So previously our focus was only regarding safety. It was only reactive in nature. Now we have shifted to proactive and predictive safety. So for predicting, we are relying on the AI systems. AI-based monitoring and predictive maintenance is our focus in the future direction. For that, we require smart sensors for anomaly detections, such as thermal, vibrations, or arc. Automated emergency responses, that is, whenever an emergency occurs, the system has to isolate itself, as well as it may require shutdown. So global trend is towards zero harm workplace. Worker as well as equipments have to be made with zero harm to it. So safety as a core business value, the market is rising in such a direction. As I had already discussed in the previous session, the major electrical hazards are the electric shock, arc flash, arc blast, fire, and equipment failure, which can cause up to explosions. So we need to mitigate the hazardous elements. So we have to implement or incorporate protective devices, which were already discussed in the previous session. And as a future trend, we are doing the predictive monitoring by using the thermal imaging, the partial discharge, vibration analysis, etc. As a part of engineering control, the grounding, barrier, insulated tool, the testing and maintenance of tools, those are required. And administrative level, we had discussed that LOTO, that is lockout and tagout procedures, have to be followed, and regular inspection has to be done. Despite these particular strategies, we have to make sure that our PPE is selected as per the ARC ratings, and proper insulated gloves along with face shields have to be selected. The workers have to be given proper training, and a safe culture has to be developed within the industry for preventing a hazardous situation or accidental situations. So, as I had already mentioned, the mitigation methods which I employed for electrical hazards are these. I had already discussed all these things, so I'll be just scrolling through it. Smart earthing and advanced monitoring, the remote operation and tracking system. And now all such protective devices or mitigating devices are developed in various countries, and as the statistics show, over 1,000 electrical workplace accidents occur annually in developed countries, and out of this, more than 30 results in fatalities, highlighting urgent need for enhanced safety measures. So the market for the safety measures, safety equipments are growing at an increased rate. So globally, the electrical safety product market exceeds more than 25 billion USD in 2024 and is projected to increase at 5.9 percentage through 2034. So the product growth, we can see the personal protective equipment, the largest segment, generating around 10.1 billion USD in 2024, driven by advanced materials and smart monitoring capabilities. And the smart safety technologies, which incorporate IoT-enabled devices as well as AI-powered monitoring system, represents fastest growing segment with 25% annual growth rate. The graph shows the safety product market growth in various with respect to various equipments and training programs. So the key industry safety metrics, the incident analysis, the technology adoption, and regulatory impact. The incident analysis, we can see that comprehensive analysis reveals key patterns in electrical safety incidents across industrial sectors and geographic regions. 70% of fatalities occur in the non-electrical occupations, mainly it is in the construction field. And arc flash incidents represent 80% of injuries when we consider the electrical hazards. Technology adoption. Advanced safety technologies are transforming traditional approaches to electrical hazard prevention and risk management. The smart PPE adoption increased 35% in 2024, and the IoT monitoring systems reduce incidents by 40%. Automated shutdown systems prevent 95% arc event. events. So we can see there are certain regulatory regulations or standards being followed, like NFPA 70, OSHA guidance, which emphasizes on arc flash boundaries, and global harmonization of safety standards are accelerated. So, what are the strengths, weakness, opportunities, and threats regarding electrical safety? So, strengths of modern system. We know advanced monitoring, real-time data analytics, uh, automated shutdown capabilities, and comprehensive training programs enhance the overall workplace safety. Whereas current systems, they are highly complex. So legacy equipment integration challenges, high implementation costs are there, uh, insufficient skilled personnel limit optimal safety system deployment. We are having so many developments in technology so that the safety can be improved, but skilled labors are limited, and that is a weakness when we consider the electrical safety. Market opportunities ahead. IoT integration, AI powered prediction maintenance, renewable energy expansions, and emerging markets present significant growth potentials. The threats, the automation is increasing, IoT integration is there, AI integration is there, so there can be cybersecurity vulnerabilities, and the regulatory complexities, technology obsolescence, and economic pressure challenges are the main threats in electrical safety. So we'll see how the electrical safety system evolved. Mechanical interlock era was there, where the basic mechanical safety systems with local control mechanisms provided foundational protection, but those were limited to remote monitoring capabilities. After that, we went for the PLCs, that is introduction of PLCs, programmable logic controllers, and digital monitoring enabled more sophisticated safety protocols and remote operations. Those were those systems were limited for a small area. Then we went for the network-based safety. When we went for network-based safety, there was communication between the systems. So communication protocols and SCADA systems revolutionized safety management through real-time data sharing and coordinated responses. And in the modern world, the system leverage artificial intelligence, machine learning, and predictive analytics for proactive hazard detection and prevention. So regarding advanced safety technology components, we are having smart monitoring system where the real-time electrical parameter are monitored with IoT sensors, and the data is communicated through wireless, and all the data will be saved on a cloud, and based on those data, the volume of the data will be very high. The big data analytics enables proactive hazard detection and immediate response to dangerous conditions before any incident occurs. Automated safety interlocks, advanced SCADA-based interlocking system provides multiple layer of protection through digital replication of mechanical interlocks, enabling safe remote operations while maintaining comprehensive safety oversights. So for such interlocks or simulating such interlocks, we can use the digital twins. The core technologies in modern safety system. The integrated safety architecture. The contemporary electrical safety systems integrate multiple technologies like IoT sensors, the AI analytics, automated controls, communication network to create comprehensive protection against electrical hazards. One of the main hazard in electrical system is the arc flash. So flash protection, advanced arc flash protections and mitigation systems using optimal sensors and current monitoring and ultra fast circuit interruption to prevent injuries. So, which will be acting within uh, 1 milliseconds. Predictive monitoring. So we know always uh, prevention is better than cure, right? So if we can predict any hazardous situation, that is well and good, so that we can avoid incidents or accidents that may occur. Machine learning algorithms analyze such electrical patterns to predict potential failures and hazardous conditions before they manifest as safety risk. So, in order to predict such hazardous condition, we need to collect data from different points of the system, and proper communication has to be done for that. So communication system ensures reliable data transmission and coordinated safety responses across distributed electrical infrastructures. Safety system implementation analysis. We can see that the implementation insights is based on analysis reveals varying adoption rates of advanced safety systems across the industry, with utilities leading in smart system deployment while construction lags in modern technology integration. So the manufacturing, the balanced approach with steady smart system growth and construction, the highest basic system usage and utilities lead to leading smart system implementation at 20% penetration. So automation and electrical safety. Automated hazard detection system, that is advanced sensor networks continuously monitors electrical parameters and environmental condition along with the equipment status to automatically identify potential hazards before they escalate into dangerous situation. And automated safety system executes pre-programmed responses, including equipment shutdown, alarm activation, and emergency protocol to mitigate risk without intervention of human. And with the data collected, we can have predictions of such failures which may occur in a system. Smart safety systems and IoT integration. We know the sector IoT is developing at a fast rate, and IoT sensor network, they are used for wireless temperature and current monitoring, and the cloud-based data analytics and alerting systems are developed. Based on the data, predictive failure detection and maintenance schedules can be charted. smart control centers, where the centralized monitoring and control capabilities are done. Here, the real-time safety parameters are visualized and analyzed. Automated emergency response coordination and communications are done based on the historical data as well as the present data for safety improvement. Then the mobile accessibility and field worker support. Field workers safety alerts and guidance are given. Uh, and digital permit to work and safety procedures are uh, intimated, are being communicated to the workers through mobile. Emergency communications and location tracking are also being done. AI and machine learning application in the field of safety. Machine learning algorithm revolutionized electrical safety by analyzing vast data sets to identify patterns, predict hazards, and optimize safety protocols. AI systems process real-time data from multiple sources to provide unprecedented safety insights and automated responses. So AI-powered safety system can predict electrical failures with an accuracy of 95% and reducing workplace incidents by up to 40% through proactive interventions. These are certain safety standards. Uh, NFPA 70 provides comprehensive requirement for safety standard in workplace, covering arc flash boundaries, PPE requirements, risk assessment procedures, and safe work practices for industrial electrical safety. The other regulation, that is OSHA, risk assessment framework process. For assessment of risk, first of all, it's important to identify a hazard. Systematic identification of electrical hazard, such as arc flash, arc blast, shock, or fire, through comprehensive facility surveys and equipment analysis have to be done first. Then risk evaluation and quantification has to be done. That is made by assessment of likelihood and severity using standardized methodologies. The arc flash calculation, the incident energy analysis for accurate risk determination. Based on what risk is going to occur, the control measures have to be implemented. For that, application of hierarchy of control. We had already discussed the elimination, substitution, engineering control, administrative control, and PPE selection, as well as the deployment of the control measure has to be done properly. So these are the elimination, substitution, engineering control, administrative control, and proper selection of PPE. Advanced personal protective equipment. So one such PPE is smart arc rated clothing. The next generation arc flash suit with integrated integrated sensors monitor environmental condition and worker vital signs. Advanced materials provides superior protection while maintaining comfort and mobility for extended wear periods. Then the intelligent safety equipment, that is voltage detecting gloves with built-in indicators, provides real-time hazard awareness and protection verification. Connected PPE systems enable real-time monitoring and automatic emergency alert for enhanced worker protection. The comprehensive arc flash mitigations method. The modern arc flash protection integrates detection, suppression, and personal protection system to minimize incident energy and protect personnel from dangerous electrical arc. So the detection technologies have changed. Optimal sensors detect arc flashlight signatures within milliseconds, and current monitoring system identify fault condition and abnormal patterns. Multi-criteria detection combines multiple parameters for accuracy. Once the detection is complete, we have to suppress what the anomalies. For that, the anomaly systems, ultra-fast circuit breakers interrupt the arc within 2 to 4 milliseconds are available. The arc suppression units inject specialized gases to extinguish extinguish arc. Coordinated protection systems minimize downstream equipment damages. We had already discussed that ZSI in a similar fashion. The protection systems are the damage on the protection systems are made by using ZSI. Incident energy reduction. Advanced systems reduce arc incident energy by 90% or more, and the response time has to be quick. Detecting the detection and response within 2 milliseconds prevents major incidents. So the equipments which are protecting, they should be coordinated. So coordinated system minimizes the damage and reduces the repair costs. So first of all, the hazard element has to be detected. According to the hazard element, the suppression has to be done. Suppression has to be done based on the energy as well as response time. If those are coordinated in a correct manner, we can reduce the repair costs and reduce the damage. Circuit protection technology evolution. Advanced protection systems like modern circuit protection system protection technologies integrate smart monitoring, predictive analytics, and automated response capabilities to prevent electrical fault and protect both equipment and personnel from dangerous situations. The advanced protection system are reliable up to 99% as statistics show. So the performance is very good. So advanced monitoring and detection system, I have mentioned a few. Real-time parameter monitoring, continuous monitoring of electrical parameters, including voltage, current, temperature, and power quality, enables early detection of abnormal conditions and potential hazards before they escalate. Thermal and visual inspection, there is infrared monitoring and visual inspection systems automatically detects equipment overheating, connection failures, and insulation degradation through advanced imaging technologies and pattern recognition. Multi-sensor integration system, combined sensor network utilizes vibration, acoustics, electromagnetic, and environmental sensors, provide comprehensive equipment health monitoring and predictive failure detection capabilities. So the SCADA-based safety interlock implementation, how it is being done. distributed interlock system network. A modern SCADA system enables complex safety interlocking across distributed electrical infrastructure through reliable communication protocols, redundant pathways, and real-time status verification. They replicate traditional mechanical interlocks digitally while adding enhanced monitoring capabilities and remote operation safety features. Whereas centralized safety management, it enables comprehensive safety oversight across entire electrical system, provides operators with real-time visibilities into interlock status, equipment condition, and safety boundaries. Advanced alarm management and automated response capabilities ensure rapid reaction to safety violations while maintaining detailed audit trials for compliance and continuous improvement of safety protocols. So these are certain protocols for safety. Strategic implementation of advanced safety systems, phased deployment strategy. So it's a systematic implementation approach that prioritizes critical areas, managing budget constraints and minimizing operational disruption, while ensuring comprehensive safety coverage across all facility operations. Integration and optimization. It's a seamless integration of new safety technologies with existing systems while optimizing performance, ensuring compatibility, and maintaining operational continuity throughout the upgraded process. Next is awareness and safety awareness, training and safety awareness programs. So, as we said, training the workers are very important. So, modern electrical safety training programs incorporate virtual reality simulations, hands-on exercises, and interactive learning modules to ensure workers develop practical skills and theoretical knowledge necessary for safe electrical work practices in industrial environment. And continuous competency assessment of worker has to be done. For that, regular evaluation and certification processes verify worker competency through practical demonstration, written assessment, and ongoing performance monitoring to maintain high safety standards and regulatory compliances throughout their career. These are based on the construction industry. So advanced safety systems reduces our electrical incidents by 85% while improving operational efficiency and regulatory compliances. This transformation demonstrates the significant impact of implementing comprehensive electrical safety systems that integrate modern monitoring, automated protection, and intelligent analytics. So as we go on to the automation, what are the benefits of automation in safety? It will reduce the downtime, enhance the worker protection, lower maintenance cost, and compliance with safety standards. According to the data, we can see that the accidents in industries within India is uh, reducing as the technology is improving, as the statistics show. The future trend will be on AI. So AI powered predictive analytics will be taking place, and we can utilize that for reducing our hazardous situations. Digital twins for safety simulations can be utilized so that we can reduce the costs for repair and maintenance. Where wireless safety systems and integration of all these things in Industry 4.0. As a conclusion, importance of proactive safety system. We can see in the past we were only reacting to the hazardous condition. Now it's proacting. We are predicting the hazardous condition and acting prior to the incident. So, role of automation in shaping safer industries are increasing a lot. So, safety isn't just a protocol; it should be a culture. Let us see what are the advancements in automation and safety. The first thing, the SCADA, is a real-time monitoring of substation breakers, bus voltages, transformer health, and remote operation of circuit breakers and isolators. It features alarms, event logs, predictive alerts for fault trends. SCADA is an integration with protection relays improves the coordination. Cybersecurity hardening is essential to protect SCADA system. Sorry. Next is the IoT sensors. Monitoring temperature, partial discharge, and dissolved gas analysis in transformers can be done by using IoT sensors. Worker wearable track shock exposure, the arc flash risk, fatigue, and locations, as well as wireless sensors reduces wiring costs and improve flexibility. The AI algorithm filter noises and provides actionable safety insights to the data obtained from the IoT sensors. Now, I have talked about digital twin. The digital twins are just virtual replicas of electrical network for simulation and analysis. It provides a comprehensive and real-time view of operation, enables the organization to identify, assess, and mitigate safety risks more effectively. It can be applied in many areas, and when we look into the safety, electrical safety systems, it can be used for fault simulation, relay coordination, arc fault virtual VR training. Then the digital twin also enables fault propagation analysis without risking real equipment. And it can be used for what if scenario in maintenance planning. That is, we can create a faulty situation to the virtual replica of our network and find out how we can do the maintenance. It validates safety systems before real world deployment. Advanced analytics and AI. Predictive maintenance detects anomalies before failures. Big data analytics correlates our system data and outages and weather impacts. Artificial intelligence and machine learning recognizes insulation aging patterns and optimizes load shedding also. It also helps to reduce downtime and extend equipment life cycle. So the hardware, automation hardware in safety, it includes the PLCs, relay, interlocks, light curtains, and safety nets. So safety PLCs, they are built with redundant processors and self-diagnostics. They are certified for safety integrity levels. The implementation implement complex safety logics, safe, talk off, and speed monitoring. They can be integrated with SCADA, IoT, and field devices. Uh, it's common in chemical plants, refineries, and machine automation. Safety relays. Two-channel input monitoring prevents single point failures and application. It can be applied for presses, conveyors, packaging systems, and they are simple and reliable, cost effective for small systems. Interlocks, door interlocks on HV switch gears, guard interlocks on CNC machines, etc. We can see the light curtains, infrared beam creates an invisible barriers in interruption of beam, and these can be applied for robotics, assembly lines, packaging, welding stations, etc. And they can integrate with safety PLCs for configurable safety zones. So integrated digital safety ecosystem. They are unified dashboards combine SCADA, IoT, digital twins, and AI insights. The mobile integration, the safety alerts via smartphones, tablets for quick responses. About cyber physical integration, merging cyber security and functional safety. Future direction, self-learning and automation, autonomous safety systems. So we'll go for hybrid AC DC grids and renewable. Hybrid AC DC grids are common in microgrids, EV charging, and data centers. DC arcs are harder to extinguish and requires DC rated breakers and arc suppression devices. Whereas renewable and storage, uh, when we consider renewable and storage, mostly the solar is there. So solar inverters plus battery system creates multiple energy storage energy sources in the grid. So there will be residual DC energy which may backfeed even after disconnection. So safety standards evolving to cover this backfeeding or DC arc fault is required. Similarly, drones and robotics can be used for safety. Robotics used for remote breaker racking, valve operation, and switchgear handlings, and keeps operator out of the arc zones and reducing exposure to the arcs. Drones, it can be used for inspection of high voltage transmission lines, substations, wind turbines, etc. They can be equipped with thermal cameras to detect hotspots and partial discharges. This will reduce human exposure to heights, radiations, and live line hazards. Smart PPE. So arc rated clothing protects against heat, flames, and arcs. So, wearable sensors embedded in helmets, jackets, and wristbands monitors arc flash exposures, shock hazards, heart rate, fatigue of the worker, and data logging provides exposure history to compliances and risk analysis. So these smart PPE improves proactive safety measures and workforce protection for the worker. These are certain smart PPEs. So augmented reality and VR is used for training our workers at the workplace. So augmented reality visualizes hazards, safe zones, and LOTO procedures site on site, and virtual reality immersive training for flash confined spaces and fire scenario can be given for the workers using virtual reality allows safe mistakes in the virtual environment without real danger and improves worker competency hazard awareness and reduces accident probability. So these are the case studies which specifies how much we have to focus on the safety. This is one such incident which occurred on NASA in the year 2010, Kennedy Space Center. So the safety interlocks were bypassed to save time during testing, and here the root cause was the defeat of the safety system for convenience and a culture that prioritized schedule over safety. So, the key lesson from this event was that interlocks are a critical engineering control that should not be bypassed. The first incident I'm telling about. So, work around must be strictly controlled to prevent dangerous situations. So, stricter interlock enforcement were being done after this particular incident. The second such incident, this is NASA 2010 incident, and next one, the second incident is at Indian refinery in the year 2014. Where India experienced a near catastrophe when an abnormal pressure rise could have led to an explosion. However, the safety instrumented system detected the unsafe condition and automatically shut down the process and isolated the units. The outcome was that a potential catastrophe was prevented and no lives were lost. This particular case study highlighted that a properly designed SIS with an adequate safety integrity level rating is crucial for saving lives and that regular maintenance is essential for its reliability. And the third one, Stuxnet 2010, it was a cyber attack on Siemens. Uh, the event can be demonstrated as a cyber attack, which can cause physical damage to the industrial system. A sophisticated computer worm targeted Siemens PLC at an Iranian uranium enriched facility. The malware altered the PLC logic while sending false normal reading back to the operator. who remained unaware of the issues, and this caused physical damage to the centrifuges by manipulating their states. The primary lesson is that cybersecurity is an integral part to industrial safety. It showed the vulnerability of control systems and necessity of robust defenses like network segmentation and secure programming to prevent physical disruptions. So the final future direction is towards the AI-driven predictive safety measures, which can detect anomalies before the fault occurs, and self-healing grids, which will automatically isolate faults and reconfigure our network. Edge computing in protection system. Local AI-driven decisions can be taken by the protection relays. Smart helmets, worker biometrics, and exposure monitoring will improve the workplace environment for the worker. Integration of cybersecurity along with functional safety into a single safety strategy. So that concludes my presentation. If anyone is having any queries, you may please ask.
Dear participants, if you have any queries, please drop in the Q&A tool or you can ask now. Ma'am,
Yes.
ma'am, I think no queries.
Okay.
Okay, ma'am, shall we wind up this session?
Yeah, we can wind up.
Okay.
Before winding up, let me thank all the coordinators, uh, the organizers, and especially your principal and my dear student, Indu, for inviting me for the lecture. Thank you.
Thank you, ma'am.
Thank you, ma'am, for the very informative session.